All right, then let's start with today's lecture. Welcome to this Monday late afternoon. I brought you a new script. Let it in the package. Around. This is the chapter on magnetic sensors, so we'll start today. And yeah, it's an interesting chapter, and it goes right to the core of semiconductors and CMOS, and therefore it is it deserves to be in this course. Yeah, so let us look at those magnetic sensors. All right. So in this chapter, I'll give you a brief overview of magnetic sensor and the history and the fundamental of all types. Thank you. And then we'll study some, so that second part is a bit of theory. It's all based on the Lorentz force. And then we'll study some types of planar Hall sensors, some more general conclusions, non-idealities and compensation, and then vertical Hall sensors, which we have been developing strongly with Mekonas, and then some alternative devices that you will also see. So let's start with a few general remarks. Hall sensors are very important. I mean, that's a multi-million, hundreds of millions of dollar business. So it's per year. It's not peanuts. And that's nowadays mainly due to the fact that you find lots of Hall sensors in automobiles. Many switches are actually magnetic devices that switch on a semiconductor switch, which incorporates a Hall sensor so that some current is allowed to flow or not to flow, depending on the position of the switch. And that is one application that you find in many places. Another one is power management, increasingly so also in electric vehicles, where electric current flows from batteries to motors, and you would like to monitor the flow of those currents. And so how do you measure a current? Yeah, oh, you put a current meter in there, but if you don't want to interrupt the circuit, you put a Hall sensor nearby that is allowed to measure the magnetic field that surrounds any conductor. And then also the position of the motor to time the spark for ignition of the fuel in the combustion engines is also of importance, or Hall sensors are also of importance there, because they allow to measure the position, the rotary position of the motor by some magnetizable dented wheel with the magnet close by and a Hall sensor nearby that measures the number of these spikes or indicators, regularly placed indicators that pass by to determine what is the exact position, so that ignition can occur not too early, which would be counterproductive, which would let the motor stall, or not too late when it's already too late to do a full combustion. And that is very important in making engines efficient nowadays. The engines in my youth put out a lot of soot and things because the combustion was not optimal. They also put out a lot of lead. I breathed lead in my youth because that was good for the motor. And then fortunately found out that lead is not good for your health, and they stopped doing that. And they have other additions to the fuel to let let the fuel burn as it should. Then obviously you have also Hall sensors where subtle magnetic fields need to be measured, like in hard disks, traditional way of storing magnetic information with magnetic bits that can be read. Hall sensors are in use there to some extent, although giant magnetoresistive devices, tunnel magnetoresistive devices are much better in doing that. Yeah? Laser printers, consumer goods, again, or you would think, what should a Hall sensor, magnetic field sensor do in the washing machine? Is there any magnet being washed in the magnet? No, that's not the purpose. It's, again, there are lots of switches that should be well protected against humidity. A washing machine is a humid environment, and any electromechanical switch that operates by causing an electrical contact between two metallic surfaces to let a current flow, to switch on the washing machine, for instance, is prone to degradation, corrosion. And at some point, there will be so much corrosion that there will be no current flowing anymore. Then you need to replace the switch. Whereas if you have a Hall sensor can be fully packaged, hermetically sealed by how many layers you want. The magnetic field still goes through. If your sealing is not a magnetic shielding, then a magnet in a switch can be directed towards this Hall sensor to be detected as in one position or removed to detectable as in another position. The sensor is pervaded by different magnetic fields, which can be discriminated so that the machine knows what you intend to do and carries that out. And 20 years later, it still works. Yeah, so that's a big business, and the Hall plate, which is shown in the books, usually looks like that, somehow like that. It shows a plate, plate of material. I don't know, a little block cuboid with 4 sides, and then this cuboid is crossed by a magnetic field B in the vertical direction. And on those 4 sides are contacts. So some of those are called CC1 and CC2 for current contact, because in this simple image that dates already a few years ago in the book of Simon C, but schematically it's correct. Yeah, the current is sent through the device in one direction. So it comes through a contact that is visible here on the side. Oh, let me make that a little bit better in blue. So this contact here, yeah, and then of course this block has another face in the back. So this contact on the side. We have another script here, if you would like to take one, just here in the front, please. Yeah, so this contact on this left rear surface is used to inject the current, and then we have a current density J flowing here through the device, and out the current comes again through this current contact 2. And while it crosses this device, this volume, the magnetic field acts on the charge carriers that are carrying that current, and via the Lorentz force, by some subtle effects that we will discover, a Hall voltage, VH, appears between the side contacts SC1 and SC2. Now, people very often have these, I mean, there are some animations out there on the web, yeah? Don't look for them, but I'll show you what they show, yeah? They show kind of in perspective, beautifully made. I mean, it's beautifully made, but it's really utterly wrong, yeah? So what it shows is that, okay, this device has a contact here and here, yeah, and then the side contacts here and here, so current contact 1, current contact 2, yeah, and then the current flows here, yeah, and then you see little balls flowing, yeah, the electrons are little balls, as we all know, yeah, billiard balls, and then they flow through this device in this central channel, yeah, concentrated, like if you had a hose of water and were injecting water through the device, and then if you aim well, it goes out through the other hole at the end, yeah. I mean, it's outrageous, yeah. And then comes the magnetic field, some magnetic field, this B going now out of the plane into your nose, and then they say, ah, yeah, those electrons are deflected by the Lorentz force under this Q. So let's say the electrons flow from left to right. Okay, then V cross B makes what? It makes something in this direction, but we have minus Q in front. So they're all deflected upward. So let me show that. They're all deflected upward. And then we have this current flowing, so yeah, in a deflected way. Yeah, ha, ha, ha. It's wrong. Yeah. The current spreads over the device as soon as it enters through contact one, and then it tries to fill out the device in order to minimize the resistance that it experiences. Yeah? And doing so, it intuitively solves Laplace's equation. That's an equation that needs to be fulfilled by any current density. Laplace equation, the current, the divergence of the current density is zero, and it spreads out, yeah, in a way that ultimately solves Laplace equation, and that the object or the quantity behind is the potential, and therefore the potential solves Laplace equation. And then there are potential lines that no, let me draw them in blue. Potential lines, equipotential lines that look somehow like this. Yeah, so maybe like this, and then like this, and then again here around in circles, and then more concentrated. And this is how this the current will flow right from the beginning. It fills the whole volume. Of course, it's a little bit denser in the center, and so there is no space for the current to flow where it didn't flow before. And the only effect, or the main effect that happens in all these technical Hall sensors, is that after the magnetic field B is switched on, the current still flows like that. It is hardly changed in its flow pattern. However, what is changed is these are the equipotential lines. The equipotential lines become oblique. Yeah, so somehow oblique, and that means that there is another potential on this contact than on this contact, which may be the potential here, and here we have the potential from here, and so there is a difference in potentials. That is the Hall effect in Hall devices, and we'll have to discover how that works in more detail. And so here you see an example of a Hall sensor from a nearby company, Micronas, an old example. I think it's about 20 years old, this chip, HAL something 400 or 800 or so. And you see a lot of digital circuitry, some analog digital circuitry, of course. And then in the center, you have some quadratic looking devices. And so these are the Hall elements. There is more than one Hall sensor in there. There are, now, let me speculate. There are 2 times 4 Hall sensors. So there are 4 Hall sensors here, and then there are 4 Hall sensors there. And then those are connected together in an intricate way that allows to compensate some effects that are not desired. For instance, asymmetries, geometrical asymmetries are compensated. And the thermoelectric effect is also compensated. Imagine that one side of the circuitry heats up more than the other side because there is more calculating power going on. So more heat is dissipated there. There's a temperature gradient from left to right, or right to left. And then those semiconductor devices experience a thermal gradient, and you have semiconductor metal contacts. And if those metal contacts are not at the same temperature, you experience a voltage difference due to the temperature difference at these contacts. That's a thermoelectric effect. And that needs to be compensated away for all possible directions of the thermal gradient. So having more than one, actually 2 is good, 4 is better, and maybe they have 8 here. So, okay, so when we look at such a device, I mean, this picture is nice, but again, not only is this video animation that you find on the web totally wrong, but of course, this is only a functional schematic. Yeah. In reality, yeah, nobody takes a piece of silicon in this plate shape and then somehow puts some contacts on the four sides, yeah, with conductive saliva or somehow. No, these are produced by the process steps that are available in CMOS technology. What you need is a conducting region that has this shape of some, some block, with a thickness and then a length and a width. How do you do that? You make an end well here, an end well in a P substrate, P silicon, yellow on blue. Yeah, it's not ideal. I could switch back to black. P silicon substrate. And then there is an N well implanted in there. The same N well that can be used to fabricate some P-channel devices, P-channel FETs in it, as we have seen in chapter 2 at the beginning. Now, those N wells are usually a bit deeper than the microelectronic circuitry N wells. There are N wells that have, let's say, 3-4 microns of depth, which would be an overkill for microelectronic circuitry. Matthias, we have a new script here, if you would just like to get it. And am I actually a recording? Pause recording, stop recording. Am I recording? Yeah, I can start recording, so I must be recording. Have you heard recording starts before? Yeah, you did? I can't remember. You know, I hear that so often during the week that I don't know when I heard what. Okay, I'm glad. Somehow we should see it somewhere. Huh? Okay. Yeah. This little red dot says it. Yeah, thank you. Yeah. So this depth here, as I said, is maybe, let's say, 3 to 4 microns. Much more is difficult to fabricate, but that is the depth that is used in so-called high voltage technology, where, you know, tens of volts need to be dealt with in microelectronic circuitry. So it's not an exotic thing. It's just that not all CMOS technologies have those deep wells. So if we would like to draw or design a Hall sensor in a CMOS technology, you have to look out for high voltage options. And that may cost a little bit more, but at least you'll be able to do that sensor. And remember, in the example of Austria Mikrosysteme or the other fab, X-FAB, they had these high voltage options. So they can do that. And sure enough, Micronas must have that too. So then this device here is contacted at certain locations. So you see here a contact. It says obviously some greenish region. That must be a highly N+ doped, N+ contact. So, and then we have some silicide on top, and then the metal 1, for instance. So we have one contact on one side, a second contact opposite, and then a third and a fourth contact. And if you look at this device from the top, you see a square device as the squares that you saw before on the CMOS chip, and then it has its contacts here in the edges, 4 contacts. So that is already quite a distinction from these big contacts on one side, the current contacts on either side, left and right, and then these subtle little non-intrusive voltage contacts. And the reasons will become clear later, because any of those contacts during the operation of the device becomes a current contact. The current can be sent now through the device diagonally like this, so if I draw the current like this schematically, then those are the sense contacts, side contacts, sense contacts. And then in another cycle of the measurement, I can rotate the current vector by putting in the current from another corner, extracting it somewhere else, and then I have the other pair for sense contact, and then I rotate, duck, 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 duck. Yeah, this is called the current switching technology, or current rotation method. Yeah. Yeah, then so here we are looking at two of those contacts, maybe in a cross section that goes, through here like this from A to A prime, yeah, with vertical cut through along, let's say, along this line. Yeah, that is possible. And there is a little difference. You see here, we only have one via shown. Via is this place where the metal pierces this dielectric material to reach the silicon contact, the contact to silicon, the silicide. Yeah, there is only one shown, whereas here we have obviously something, bigger. Yeah, we have 2 by 2 such vias. Yeah, the vias have all the same size. Yeah. The company doesn't make via type 1, via type 2. They're all little holes that are reproducibly fabricated, as we also discussed in chapter 2. So this is not a true cross section. It's only a schematic cross section of what we see up here. And then what else do we have here? We have a central region that is covered by a P+ implant. So we have P, we have N, and then we have P+. So the N region is squeezed between P substrate and P+ top layer. And that simply allows to have two PN junctions, with some depletion layers, and then I should draw a second depletion layer down here. So woof, 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 that's where nothing flows. And then in this central region, the current flows between those PN junctions. And the reason for doing that is that actually PN junctions are kind of smooth. So a current can flow smoothly through. It's undisturbed by the sides. Whereas if you didn't have this reddish part, this P+ implant, you would have the current flowing right underneath the oxide. The oxide, some dielectric material, and that dielectric material has an interface that is far less smooth than a PN junction, and then the charge carriers that flow along scatter and they experience noise, and so you're obtaining a sensor that works, but it's a more noisy sensor. So your resolution will be more limited than if you have that P+. Nevertheless, many sensors don't have that P+ in there. Because, I mean, you don't maybe care about the noise because you're not at the limit of the signal to noise ratio. And then this P+ needs to be contacted also, of course, by some to be put at the right voltage, because you would like your PN junctions to be reverse biased all over the place. So your contacts, current contact 1 and current contact 2, and the potentials that are applied there need to be at a level with respect to the substrate contact. There is somewhere there is a substrate contact, some other metal, some other diffusion, that contacts the substrate, and then there is this top layer contact, and the potentials need to be applied correctly. So if you know how to drive a PN junction into forward bias. Now I always have to think now which voltage you have to apply to the P with respect to the N part so that it is in forward bias. P must be more positive. You are the electrical engineer or microsystem engineer, I don't know. Must be P. So let me think. I'll show how I think. I can only think with drawing. So we have a PN junction like this. We have a Fermi level like this. This is the P part. This is the N part. In order for this to be in forward bias, this needs to move up so that the the junction becomes narrower and the voltage step becomes smaller. So that means that the potential, no, the energy of the electrons on the n side needs to be increased, which means that the voltage needs to be more negative, because minus Q times voltage makes the energy of the electrons. So the voltage goes down in forward direction. So this is forward. So that means that P must become more positive, and then you're in forward direction. Okay, so my guess was right. And you would like now in this device, this contact, this N contact, not to be biased in forward direction with respect to the substrate and the P plus implant. So it must be less negatively charged. It must be become more positively biased, so that we're really in reverse bias. But then with the CC1 and CC2, you can choose, you can play, you can make it more positive and even more positive, and the difference is what drives the current along this device. So, yeah, and then of course you need some masks. So there is an N-well mask in here. There is a mask to define the field oxide. So here we have Fox, this whitish thing here and here. That's also field oxide, same on the right-hand side. That needs to be defined by the low-cost process. You all know about that. So there needs to be a mask that defines oxide everywhere, and these little how would I say that, belts around the contact regions. They are seen here. Then we need some N and P plus implants. I think we may need two masks here. Could be. So here, these N plus contact implants and this P plus contact in the middle. Then we need some regions that need to be silicided. So for instance, these contacts need to receive silicides, or need to be silicided where the future vias will be. But then also we would like to contact this P plus region, this reddish region, not in the center, but along the rim, like indicated here by these little dots that indicate the via contacts, the P plus contacts. And then, a grayish layer is deposited. It is opened to open these contact vias. That's this here. And then a metallization is deposited to contact whatever is below. And then we're done to this point. And then comes another intermetal dielectric, the second metallization, and the passivation if it's just a two-metal process. You have seen that in chapter 2. And what you see from top here now is let's say the contact of these corner contacts of the N-well, they stop here, and then there are also some rims, some contacts around, that make it sure that the reddish region is contacted everywhere on every side. This continues here, and this continues here also, and this is of course ended here. And so you think, well, how do we get to these metal contacts? Of course, there is the intermetal dielectric with another hole up here, and then we have metal 2, M2. So this might be, if this is M1, and let's say this is also M1, then we have a second metallization that goes over metal 1 to reach this region, and of course this here needs to be also connected to some potential, to some part of the circuitry, either in metal 2 or metal 1. I don't know, somewhere there might be another transition to metal 2 also. So this is how the device looks, and now there are alternatives that you see here. For instance, here with a field oxide, so this is the noisy version, but it still has something good on it, namely a polysilicon with silicide cover to at least insulate it electrically from the noisy environment. This is kind of a Faraday cage built around, at least on one side. And and the current now only has one p-n junction on its lower side. So, and then here we have a p plant with a full width silicide, so that makes this even more conductive. And then we can probably do with a single contact on one side or some simpler contact geometry. So this is how it is done in CMOS. And then you have some bipolar technology version also, because that has also been present in the history, at least, of the devices. I don't think any of the commercial producers of Hall devices use bipolar technologies now, because just of the fact that in order to do meaningful circuitry, you need CMOS anyway. So it's the bipolar technologies often used some epitaxial N-well, epitaxial N layer on top of a P substrate. So you have P substrate for all the thickness of the wafer, and then there is this N layer extending over the entire wafer, and then you can, by a P implant, define a rectangular area that is N-well, kind of an N-well, an N region surrounded by P walls with a P bottom. So this is again isolated all around by a PN junction that is neatly shown here in both regions, with the metallurgical transition indicated by the solid line. That's where ND is equal to NA, just at this line. And here ND prevails, and on the left side NA prevails. And then in this N layer, of course, there are some additional diffusions, N plus here, and then those are also N plus, of course, for sure, N plus also reaching into the device. And this, so schematically shown here, this is all deep, and so these are then the contacts through which current flows into this N layer and out of it again, and then you have these two devices. And again, this figure shows that it's an old schematic, because nowadays, with this idea of current switching, nobody would draw a device that is not symmetric. So what are magnetic sensors good for? Of course, for direct measurements of magnetic fields. If the magnetic field has an effect on the charge carrier transport, a galvanomagnetic effect. Galvano means voltage, magnetic means magnetic. So voltage magnetic effect. The magnetic field makes some voltage. This is galvanomagnetics. So you can exploit this galvanomagnetic effect to measure the magnetic stuff. And for instance, the Earth magnetic field is an ubiquitous magnetic field with an intensity, a field strength of 20 to 60 microtesla. Is that a lot? Not so much, not so much, because the magnets with which you live, these little magnets that you put on your, I don't know, fridge, to fix a little piece of paper, those have half a Tesla or a Tesla. It's not micro, it's full Tesla. And if you put two of those together, they're sometimes difficult to separate, at least the stronger ones. Technical magnets can be made so strong that you have really difficulties in separating them. And so the fact that magnetizable objects don't fly through air under the effect of the Earth magnetic field gradient, so then that shows that it can't be too strong. And you need a pretty delicate instrument, a compass with a needle that needs to be really hinged well on a support, made with a ruby earlier in my youth, little ruby, synthetic ruby, so that this rests and doesn't have any friction, can orientate itself in the magnetic field. Well, that's a weak magnetic field. And it's tough to measure these weak magnetic fields with silicon Hall sensors, I admit. So compasses just with a silicon sensor, as I described, are difficult to fabricate. Because noise in circuitry is easily of the order of microtesla. Sorry, these signals produce Hall signals, as we will learn how to calculate, of the order of microvolts. And then the circuit designers, the analog circuit designers who should then extract the signal from, you know, the noise or offset or so, they don't like microvolts because that's really small. Yeah, they would like to have millivolts. Microvolts limit. You can do it. Yeah, you need a lot of compensation circuitry, and but it's hard. Then magnetic recording media have typically 1 millitesla or so. Yeah, so these magnetic recording media, hard disk tapes. Barcodes, some cards are 10 millitesla, credit cards also. So that's okay if you have a small Hall sensor in those machines where you put in your banking card. If it's still read out by the tape and not by RF, then that might be a silicon Hall sensor. And then, of course, technical magnetic fields cover the full range up to Tesla, and then up to 30 Tesla, and even 100 Tesla can be produced, but that's only exceptional. Only a few labs are producing that. 30 Tesla is also pretty strong. If you go to the MRI, magnetic resonance imaging, to the doctor to, you know, identify some deficiencies, some broken bone or so, other things, inner bleeding or whatever. Yeah, tuck, 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 tuck. Yeah, unpleasant experience. I don't know if you have experienced that in your life so far. Happy are you? But lucky will you be when you can do that, because it's a way to look directly into your body. Yeah, and it's magnetic resonance imaging. Yeah, uses the precession of the atomic nuclei. They all carry a magnetic moment, and so in strong magnetic fields, they precess at a radio frequency that can be measured, and then they're by some auxiliary fields. Pung. So first they're aligned in a direction, and then pung, by a pulse field, they're all put at the right angle, and then they precess like crazy until they're again they have relaxed their energy, and that pulse that comes out carries information about where those and how densely those spins sit. Formerly, this method used to be nuclear magnetic imaging or something like that. Then people started no longer to go to the doctor for that, because they thought nuclear must be radioactive. You know, it's very dangerous. Nuclear is not good. This is the atomic bomb. You know, I don't know. Yeah, no, it's just the processing nuclei. Yeah, Kerne, Atomkerne. Yeah, that do nothing else than precess with their magnetic mode. And it's the hydrogen atoms who do that. Yeah. You don't have a hydrogen bomb in those machines. So those machines are typically 3 Tesla, some are 7, the more advanced ones. And then there are really record machines that reach 30 Tesla. And it's really hard because you need large currents through superconducting structures that need to bear the tremendous forces that come with these currents. A current acts on, causing a magnetic field, acts with a force on the current itself, and or on currents on neighboring current loops. Yeah, so the machine wants to fly apart. Yeah, so you need these huge mechanical structures to keep these magnets together. You need superconduction, cooled down to helium temperature, which is technically also challenging. So these machines are really prodigious feats of technology. And then in 1 or 2 labs around the world, they reach 100 Tesla, but only in pulses. Yeah? So they charge up huge condensators, and then the whole energy goes, for a short while, and everything heats up, and before everything melts, the pulse is over. So, yeah, but in addition to these direct measurements, we also measure indirectly. The magnetic field carries information about, for instance, electrical quantities such as currents. A current wire, through which a current passes, is surrounded by a magnetic field, by a circulating magnetic field. This circulation of H is actually proportional to the current that passes through the current. So that's Maxwell's law, which, and now if you're smart, you put a Hall sensor here. So this is a chip, and then there is a little Hall sensor here in the center surrounded by circuitry, and you measure that H, and if that H is strong, you know there is a lot of current flowing, and if there is no H, then there is no current flow. So that's how you can measure a current, and people move more and more to so-called smart meters to measure the electric consumption of households. Instead of having these electromechanical devices, these discs that spin depending on how much current you consume, that I looked at in my youth, probably you too, because that's still one of the very widespread method. The spinning speed of that disc counts the electricity that is consumed, current actually, and this is replaced by more and more non-contacting methods, so-called smart meters. Smart meters are also used to measure gases. Those are also called smart meters, but I mean them here as a Hall sensor. So you can power measurement, you can use them as overload protection, and so on. So safety can be implemented. And of course, you can also measure mechanical quantities. So if you have an object that, let's say, I don't know, has some shape, and it is magnetized, there will be maybe more concentrated magnetic field lines emerging here. And if you move with a Hall sensor again over this object, you can count the number of steps that you have passed by, and therefore you can know something about the position. It's very simply very schematic, but that's the general idea. For position, for changing position, for velocity, for angle, for angular velocity, etc. As in the motors. So here's again the information on the top of the last page here in graphical information, and then in terms of magnetism, electromagnetism, you know that we have these two fields, the B and the H, and then there is big confusion, because every brand of engineer and scientist calls them differently. So here's a collection of terms that you can find. The electrical engineers like to talk, so let me move this H here. Sorry, in terms of B as the magnetic flux density, and then the magnetic field intensity is H. For electronics engineers, you magnetic induction, applied mathematicians also magnetic field strength, auxiliary magnetic field, magnetizing field, magnetic field. So this should move up to here, and this should move up to this position. That's an old one. So I'll talk about B and H, okay? Then there is no confusion. So the B is responsible in the Lorentz force for doing something to moving carriers. If a carrier, little positive or carrier with the charge Q, moves in a direction V, in a direction pointed out by this vector V with a velocity V, and there is a magnetic field. Why don't I show it in this back direction? What will that V in this B do? It will be deflected, it will experience a force that is proportional to the velocity, proportional to B, and proportional to Q. But it depends on the relative direction of B and V. This cross product says that if V goes in the direction of B, nothing happens, because then the cross product is zero. If V is perpendicular to B, then the effect is maximum, like here. So if we have here a right angle, then V cross B makes something which points in this direction. And if the Q is a positive number, positive charge, an elementary charge, then this object carrying this elementary charge will be deflected in this vertical direction. That means that this velocity is not going to stay constant. The particle is accelerated in this direction. F over mass is acceleration. And so there will be a movement that will then lead it in circle around that magnetic field. So the magnetic field pervading space, pervading this orbit, this cyclic orbit, is then the result. If you let the electron flow freely. Now, an electron in a semiconductor doesn't have time to make a complete loop. After a very short time, it already scatters. But it is enough for this electron to be deflected ever so slightly from its straight original path. And this ever so slight deflection makes that actually where you would like to send the electron by an electric field results in a flow of the charged particle that is slightly different from what you would like to have. This is the fundamental effect that is playing here. And what I don't want to say, so these collisions, are absolutely essential, and we'll try to get a grasp on those phenomena. So based on this Lorentz force, many different effects are possible. So of course, there are insulators in which the Lorentz force does things to not moving charges, but there are also charges, and so they also experience a Lorentz force in these orbitals. And so you can have what is called the Faraday rotation or the Kerr effect in dielectric media. You send in, you have this material, transparent, for instance, you send in a polarized beam of light, and then normally this goes just through and comes out with the same polarization at the other side. But if there is a magnetic field, then whatever periodic motion occurs in this dielectric material causes some response to the magnetic field, and that is then added to the propagating electromagnetic field, which means that the polarization plane is shifting as a function of propagation length by something called the Verdet constant. It's a very important effect. If you go to Carsten Buse's lab, our optics guy, in particular Ingo Bräunig, he explores these things. Then we have the more traditional materials, conductors and semiconductors. And in conductors, you have some magnetoresistance, some magnetostriction, but the Hall effect is not so strong. It's in semiconductors, it's quite interesting, because you have a very strong linear effect and then a less strong quadratic effect. The magnetoresistance, like in the conductors, but this linear effect is beautifully, masterable, and it manifests itself mostly, or technically most relevantly, in the Hall voltage. That is what we have seen in the first schematic slide, this Hall voltage that develops perpendicular to the current flow. This carrier deflection thing can occur in very weakly doped samples where charge carriers are pushed a little bit on one side, like also in magnetoconcentration. But this idea of the water stream, the hose, being deflected now by the magnetic field, can't be realized so easily. You could maybe imagine a current an electron current in vacuum being produced between an emitter and then a plate that accelerates it, and then there is this current beam of electrons going, and then you measure the magnetic field by detecting where it ends on a screen. Yeah, you might do that, or you have another series of holes, and where they come out, you know that the magnetic field is 0 or 1 or 2 or 3 or whatever millitesla, yeah, or minus in the other direction. Yeah, we can imagine it. Yeah, it's conceivable, but it's not practical, I guess. Yeah. So now we have to deal with some fundamentals. Yeah, and so the fundamental of anything electromagnetic is Maxwell's equations, and so we have here two equations that are good to remind. Yeah, namely this B field. This B field is a divergence-free field. The divergence of B is 0, and this is nothing else than to say there are no magnetic monopoles. There are no magnetic charges. If you have seen a magnetic charge, tell me, then we'll win a Nobel Prize for it, or you will win the Nobel Prize, because people have been looking for magnetic monopoles, but they don't exist, don't seem to exist. And it's not like the electric monopoles. Are there electric monopoles? Oh, there are lots of those. Electric charges do exist. The electron is one, the proton is one, the neutron is not one, but is plenty of them. Yeah, and that is expressed in another Maxwell equation that says divergence of D is not 0, it's equal to the true charges, the density of the true charges, the free charges actually. Yeah? I think that we should say that is true. Free charges, mobile charges like electrons also. Yeah? And then this H has the property that its rotation, the rotation, this is the rotation of H, is equal to the current density, the true current density, the electron or hole or whatever current density, true charges. Actually, I should say electrons or protons. And then there is another term that is called the dielectric displacement, and we take here the time derivative. There is another equivalent in Hall's in Maxwell's equation that reads rotation of E is equal to, and now I say nothing, and then I say plus dB dt. So here you have the field that you find up here, down here, and here you have the current density that corresponds to the motion of those carriers. And now translated, we take the other field, take its rotation, and then we have here the true magnetic charge current density that doesn't exist because there are no magnetic charges, so there's nothing here, plus the time derivative of the one that is up here. So this is symmetric, and the symmetry is only broken by the fact that there are no magnetic charges. If we had them, this would be fully symmetric, and then we would have some other forms of electromagnetism, not fundamentally different from what we have here, but it would just be enriched. And so then these are the naked equations, and then there is a relation between B and H actually, and that depends on material. So in vacuum, B is equal to mu times H, mu 0, where mu 0 is the vacuum permittivity. Now 4 pi times 10 to the minus 7 volts second per ampere meter. Funny units. But in materials, materials somehow enhance one of those fields, namely B. In the presence of H, B must be stronger, and then there is this relative permeability, magnetic permeability, mu R for relative of the considered material. So you have highly magnetizable materials that have a mu R of 1,000 or 10,000 for antennas, for instance, and then the B is magnified by that material, which can be very handy. So then, in addition to these mu's, we also have mu without an index, or later this will have the index n, and even h, and that will be the mobility of charge carriers in a solid. So mu n would be the mobility of electrons, of the n carriers. Mu h is the Hall mobility, and I could add comma n if I wanted to say the Hall mobility of electrons. So those mu's have the units square meter per volt second, and when you know what Tesla is, this is just inverse Tesla. Now it's not an inverse car, it's Tesla, the inventor of a lot of electromagnetism and experimentalist, and then he also had some theories which survive in esoteric circles. Amazingly, Tesla is credited for incredible things, that he never said. The scalar field. I have a professor in Furtwangen who has made theories about Skalarwellen. Nonsense. And some, Tesla tried to solve Maxwell's equations, and then he was a brilliant guy, and he put forward some methods, which then finally were not so successful because other methods were more successful. But yeah, I get confronted with such bullshit from time to time. It's hard to counter argue. So what else do I want to say? So interesting, it's Tesla, and the amazing thing is that B, the units of B are Tesla, or I should say volt second per square meter. So that mu times B, a mobility times B, the unit of mu times B is nothing, a number. It's unitless. And you will find mu times B everywhere as the main parameter, as a central size parameter of how strong a magnetic effect is going to be. B alone cannot do anything. It's because carriers can move that B manifests itself in a magnetic effect. So it's mu times B. The motion of the carriers doesn't do anything. It's because B acts on them, and mu times B is kind of the package that says it. And so now when we look at any charge Q, arbitrary Q, the force that is acting, the electromagnetic force that is acting on such a moving charge Q is Q times E. That's the effect of the electric field on Q. A positive Q is moved in the direction of the electric field. We know that. It's accelerated. And if it's accelerated in a current conductor, in a conductor, then the charge is moved and moved and moved. It collides, and then it accelerates again. And the motion of all those charges is the current. So that's absolutely classical. And then we have here the second term, which is the Lorentz force, which we just saw for this charge Q. Velocity and electric field. Electric field has as unit volt per meter. It's a gradient of a potential. Volt is the potential, and then the difference in voltage per meter is the gradient of the potential, and E is proportional to that voltage gradient. So if we do that with an electron has charge minus Q, so the capital Q would be minus Q, and then this is true. That's the total force of this moving electron. With the elementary charge 1.6 times 10 to the minus 19 ampere second. And now we come to these mobilities, Yeah, they will be important. What is plotted here is the mobility now in not square meters per volt second, but in square centimeters per volt second. So if you would like to have the square meters per volt second, you divide by 10,000, and then this corresponds to about 0.14 square meter per volt second. So that if you multiply mu times B in this region for a B that is 1 Tesla, like your household magnets now, these powerful household magnets, what will you get? 1 Tesla times 0.14, yeah, this is 0.14. So it's a number that is smaller than 1, but not dramatically smaller than 1. It's not 10 to the minus 16 or something. Yeah, it's of the order of 1. Yeah? So with a Tesla, mu times B of a semiconductor like silicon that is shown here produces some decent effect. Yeah. At another doping here, down here we have the doping, the total impurity concentration in the well, which may contain acceptors plus the additional donors that we put in. For instance, if it's an N well, to overcompensate the acceptors, let's say this is, if this is doped overall to 10 to the 17, let's say 1 times 10 to the 16 of acceptors and 9 times 10 to the 16 of donors makes 10 to the 17, then the mobility of those electrons is going to be 700, only half of the maximum that you can obtain here. If it's very highly doped, the mobility goes down. And since mu B will be the important parameter, it's already clear from now, from this picture, that it's better to use electrons as the carriers to exploit the magnetic effect, because then mu B will be larger than if you do it with holes that have such a small mobility, 3 times smaller. So that's only quantitative. Qualitative will have to make this quantitative. Why this mu B is such an important parameter. What else did I want to say? And of course, it's good to have not too highly doped regions in order to have more mu to exploit than at highly doped semiconductors. So now some more fundamental theory. So with B equals 0, what do we have in a semiconductor? Let's take an N semiconductor, therefore the carriers are electrons, and let's assume that there is no concentration gradient. So a homogeneous conductor. N is the same everywhere. Then what is the current density J? The ampere per square meter per second that flow through a cross section. So we have a cross section, we have amperes flowing. Ampere? No, that's not right. The ampere per square meter, which is charge, Coulomb seconds, ampere. What am I doing? Ampere second is Coulomb. The Coulomb, so Coulomb per square meter per second. This is ampere. And now these ampere flow per square meter of cross section. That's the current density. And we all know that the current density is proportional to the electric field. If we apply an electric field to a conductor, a current will flow, current density will flow, and that is going to be proportional to the electric field. That's Ohm's law. If you have more electric field, due to more voltage difference between contacts, then more current flows, more current density flows. If you reverse the electric field, the current flows in the other direction. If you have no current, no electric field, then no current flows. That's comprised in this sentence here and in this equation, and the proportionality constant is called the conductivity. So that is usually just a number, because J and E go in the same direction in isotropic materials. And this is true also for silicon in the absence of B. So you can also write this sigma n0 as an identity matrix times a number. But this identity matrix acting on sigma on A doesn't do anything. So why not just use it as a constant, sigma n0? So one is bold here. This is bold. It's a matrix, and it's also matrix here. And here we have a non-bold sigma, which means that it's just a number multiplied by this matrix. But actually the number itself is good enough. So and this this number sigma n0 is equal to mu of the electrons, the mobility of the electrons, times the density of the electrons, times the elementary charge. That is a fundamental result from the theory of conduction. So now what happens with B different from 0? So just in a simple picture where you can imagine this J having been before defined. So let me write the, well, actually I'll write it differently. Where is the eraser? Oh, that's small. Make it bigger. So let's look at this again. We have the current density vector, which we call Jx, Jy, Jz in the 3 directions, and we have here Ex, Ey, and Ez. And this vector J is proportional to this E, which we can write as sigma n0 times the matrix 1, 1, 1. The identity matrix. And so the result is that if we switch on B, no B will not change anything. So that's the result without B. But as soon as we switch on B a little bit, and not too strongly, so that mu n and B is still smaller than 1, then we can simply change these off-diagonal terms. What is 0 here becomes non-zero, and this is shown down here. So this matrix, the bold sigma n0 now becomes this sigma n without 0, which is this number sigma n0 times a matrix that has still the ones in the diagonal, like here, and then it has some off-diagonal terms. Something which depends on the z component, on the y component, on the x component of B. And you see that it's actually what is added here is not a symmetric, but a so-called skew symmetric or anti-symmetric matrix. It's one that has in the lower half the opposite of the elements on the upper half. So these are just obtained by multiplication with -1. Same here and same here. -1, -1, -1. So we add to the originally symmetric conduction matrix. No doubt this is a symmetric matrix. Because of the B field, we add an antisymmetric term. And actually, I did the calculation before, again, just to make sure that everything's right. And I think this matrix is wrong. And maybe Anja knows by heart if this is wrong. Anja did the bachelor thesis on some magnetic effects, and so she has been struggling with these things for some time successfully, I must say. And so I think it should be minus, plus, minus, and then plus, minus, plus here. Yeah. So we'll let it stand in yellow. Yeah. This is the latest version. Yeah. Probably it switches every time I look at this matrix. Yeah. It's minus, plus minus is always a pain in the matrix. Yeah? So let's look at now what some other yeah, sure. Yes, yes. So the question is, so this would mean that B influences the conductivity of the material. This is a way to express it, because an E field produces a resulting J that is no longer the same J as it was without B. Because now we have these additional elements. And we'll have to see how this B is modified by the action of B. What does that mean? And there are many implications, and some are quite geometric and others are less intuitive, and we'll be dealing with that for quite a few U-graphs. But your comment is absolutely right. So one step back, if we have just the electric field, then this is the force. If we just have the Lorentz force, then this is the force. And of course, now we have a total force due to both of these effects that can be written like that. Yeah? As for the case of the electrons, where Q is the elementary charge. And V is again the velocity vector with its three components, and B, the B field with its three components, and E is the electric field with its three components. And so a transport for electrons without magnetic field in isotropic, isothermal, non-degenerate n-doped semiconductors. So not depending on direction, same temperature everywhere, not too strongly doped, but n-doped. That's what this means. Is written in general as J 0 standing for B equals 0, is equal to sigma n. And actually, I can put here my n0. I should add a 0 I found today when reviewing my slides. It's better to put an n0 here. And then we have also, in addition to this drift current, we also have the so-called diffusion current, but this will be neglected throughout the rest. But for real devices, we may have to keep in mind that actually this also exists and might modify, but not at the level of approximation at which we deal here. And then it is also that the current density actually can be expressed in terms of the velocity of the carriers, namely the density of the carriers moves with the velocity, with the drift velocity V, and it carries a charge per carrier Q, and that makes this object here. Q times V times N, and because the charges are negative, it's minus Q times V times N. Yeah, and let me put this 0 also here. I will add it a few times. I think it's more consistent. And then we have also here the D, that's the electron diffusion constant, and N is the electron concentration, the density of electrons, the number of electrons per cubic centimeter, or just per cubic centimeter as it is usually written, and the electron drift velocity. So now, if we take this equation, this equation here, and now instead of E, instead of sigma NE, we write, instead of the E, we write, instead of E up here, due only to F1, we write in what we have here, the F, so this E is F1 over minus Q. And now, instead of F1 over minus Q, wherever E stands, we write F of due to E and B
yeah, divided by minus q. So this is what is meant by this replacement. Wherever we have E, formerly due to F1 over minus Q, we write now F of E and B over minus Q, and then it has the sigma n0 in front everywhere, and I add the 0 everywhere. Yeah? So that's quite fine. Yeah, and I should also add it here. No, and this is again crossed away. Yes. Oh, low battery. Interestingly, I'm preparing everything. Yeah, but now you know already my system. Yeah, that I still forget. You're saving me. Thank you. So now, of course, the V we have here is a V that depends on B. Yeah? It's not the V, the velocity of the charge carriers without magnetic field. It's whatever comes out and under the effect of B. So I'm writing here on purpose V of B. And now we can proceed several ways. For instance, what is proposed here with this equation from before, here, we can in analogy we can write JB. Now this is the current because of carriers moving velocity VB, and if I just multiply n with minus q, that's what I should get. And if I add another mu n in front, here on the left and right, actually with a minus, then I obtain this equation here. And this equation allows me to replace the sigma n0. Of course, I have to add my n0 also. Can replace the sigma n0 times v by minus mu n JB. And if I do that, replace it here, and then also replace this here by J0, then I obtain an equation that tells me where the current flows in the presence of B, if I know where the B shows, and if I know where the current flowed without B. This is the current density without B. Here we have the current density with B, here also, and here we have the B that causes that J to change whatever direction or intensity, we don't know, to change. And so what we are left with here is an equation that contains the effect without B, and then what we would like to know in an intricate way. It's on the left and right. It's an equation for the unknown JB. Actually, it's an equation for the three components of JB. There's a JB X, Y, and Z on the left and on the right. So we have actually, it's a vector equation. There are three equations that connect the three components of JB with the three components of JB on the left and right. But with this cross product. So if you have three equations with three unknowns, you say solve, and poof, it says, it solves the thing, and the solution is given on this line. And that, to calculate that, to solve this equation, that I will let you do in an exercise. There's many ways. I mean, you can write three equations, and then you can modify them, and you can write them as a standard. It's all linear. So it's a linear system of equation. So that should be fairly feasible. You can also do it the vector way. There is half a dozen of methods that allow to solve this equation. And the result is that actually the new J in the presence of B is equal to the old J without B plus something that connects the old J with the B through a cross product. So that's a linear change. And then you have another term that contains B in two positions. So on one hand, B is multiplied with this original J, 0, as a scalar product or dot product, or how do you also call it? Dot product? Internal product or something, yeah. The dot product, Skalarprodukt in German, yeah. And then multiplies the result of that dot product with B in its full vectorial splendor. Yeah. So B does influence J, yeah, but with different effects due to the components of B parallel and perpendicular to J. Yeah. If B is perpendicular to J, this term comes to bear. Yeah. Then, so if B is perpendicular to J, this is present, and then this dot product is 0. Dot product of two perpendicular vectors is 0. So this is gone. If B is in the same direction as J, then this is 0. Oh, no, I shouldn't scribble around here. Then this is 0, but this dot product becomes maximum. And then we have a modification of J0 by something that shows in that direction of J, because we just assumed that B was in the direction of J, and J is modified. But then the whole thing is also divided by a number that consists of 1. Yeah, so it's like multiplying everything by 1 plus mu B square. I should add the n here. Mu and B square. Yeah. So in addition to this 0th order term, this term linear in B, and this term quadratic in B, we have in the denominator also a term of 1st order and then a term of quadratic order in B. So this makes it a little bit complex. But for instance, if we now just keep terms up to 1st order in B, if you do a Taylor expansion of this whole thing in terms of B components and only keep what is linear in B, and the quadratic terms are kind of the negligible quantities, then we're left with those two terms only, and this can be neglected because it adds, in the expansion, another term of 2nd order, and then we just said we would like to neglect those. So galvanomagnetic effects up to linear order are described fully by this front equation. If we would like to go to the 2nd order, to have a more complete picture, we need to keep this term in the numerator, and then we also have to include this term in the denominator. And so the perpendicular component of B makes a current contribution that goes perpendicularly to both to B and J0. So let the current flow J0 in this direction. There is B vertical. As a result, there will be a current component in a direction perpendicular to both of those. Sure, like this or like that. So that means if the JB consists of this original contribution, the first term here, and then this perpendicular, it means that the B makes the current flow in this direction. We may have applied an electric field to push the current right through this channel between you students, and then boom, it hits Jonathan. Whoa. Yeah, this is how the Hall effect works. Plastic work, very tangible way. I'm sorry, this was not meant to be aggressive. Okay. It was a Hall of charmed. Okay. Yeah, and then the component parallel to B, if there is a component of B parallel, like here, parallel to the current direction. Of course, there's still a vertical one, which still causes this deflection of the current on here. but this parallel contribution has a component in the direction of the current, and that makes some current flow now in the direction of B. Complicated things. Fortunately, that second effect is quadratic, yeah, in B. Yeah? And so if mu times B is not large, this remains small. So imagine we apply 1 Tesla, and that means that mu B at the maximum in silicon is 0.14. Then mu B square is equal to 0.02, 2%. So this modification is only 2% of 1. I hope I calculated this right. About. 196. 196. Yeah. So that's why I made this here. It's about 0.02. But you are correct. Yeah. Sure. And so this is quite small. Yeah. The same for this term. It's J0 multiplied essentially by 0.02 and then some directional information. Yeah. It's a small effect. Whereas here we have something that is 0.14, 14% of the original J0 goes now in this direction. That's a major effect. And then if you think that the mobility is smaller than 0.14 square meter per volt second, it's only half of it, then this becomes even more negligible by a factor of 4. So does this term. And so very often we can be content with these first terms. But for the sake of completeness, here I present it, of course, more completely. All right. Now, I think I will stop here. It's 3 minutes before 5:30, and then I can resume that tomorrow, and we'll continue with the lecture. And then tomorrow, at the end of the day, I will probably submit some new exercises to be calculated until Tuesday of next week. I'm saying that into the screen here so that some of the participants who can only participate on Tuesday can also do the solutions and present the solutions on that Tuesday of next week. Okay, well, with that, I'm happy, and I'll continue tomorrow, and thank you for your attention. Bye-bye.